When you train deep learning in many machine learning algorithms, the momentum method is very popular. Many algorithms utilize momentum method to optimize their parameter, especially when we use stochastic gradient descent algorithm. Momentum method is kind of mandatory. Without momentum method, we can observe very bad behavior. And also, um, even without stochastic gradient descent, with exact gradient descent algorithm, momentum method still very efficient way to overcome this kind of situation where the objective function has very different curvature for each direction. For example, in this case, this direction, the y-axis have very high curvature, high second derivative value, whereas this direction, the x-axis have very low curvature, very low second derivative value. So with this objective function, what is alpha and beta? So basically the gap between alpha and beta becomes very huge when your objective function looks like this, because the Strongly convexity will be decided by the most slowly varying direction, whereas the smoothness parameter will be decided by this direction, most rapidly varying direction. Okay, so when alpha and beta has high gap, the conversion speed, because the conversion speed depends on the alpha and beta, this is called condition number. So the condition number, when the condition number is very high, beta over alpha is very high, the conversion speed is very slow, because when we say this is kappa, the conversion speed is proportional to 1 minus 1 over kappa per 2 t. When this is huge, this value close to 1, so this value very slowly converts to 0. Okay. But when you learn momentum algorithm, what will happen? So first of all, what is the definition of momentum algorithm? The momentum algorithm is xt plus 1 minus xt not only depend on the current gradient value minus step size times gradient of f at point xt, but also depend on the previous time slot update, xt minus 1. So this is a momentum parameter mu, and usually mu value in between 0 and 1. So the mu value control how much information of the last time slot or previous times we want to keep for the next time update. If mu value close to 1, then the previous time slot update will be there, remain, and we first update as much as previous update, and then update more with the current gradient vector. Okay, whereas when mu close to 0, then we we forget all the information, and we just depend on the current time slot and gradient. Right. So why this is useful? Let's consider this is the starting point. When you learn the gradient, then the gradient vector will be this direction. Okay. But since this direction has much higher gradient value, I think the trajectory will have many oscillation, and basically this oscillation make a very slow convergence. So the amount of update for this direction is very high, but amount of update for this direction is very small. But when you learn the momentum method just averages the trajectory. So first update this, and when the next time gradient is this direction, we do not simply move the xt point by the current gradient vector itself, but we accumulate the past information. Okay, so since the direction is opposite, when you compute the gradient at this point, when you learn the momentum method like this, there is some canceling effect. Okay, and the average value of the between the last time update and the current gradient will make a smaller amount for this direction, but more larger update for this direction, because this direction will share the same direction, but this direction will have opposite direction when you compare the previous time slot update and the current time slot gradient. So very nicely, with this momentum method, your next time iteration will be this. So compared to the original pure vanilla gradient descent algorithm, the benefit of momentum method is we can utilize the oscillation and boost up the convergence speed. The opposite direction will be cancelled out. The same direction will be boosted by adding the previous time slot update. So roughly the update will be like this. So you can make much faster convergence compared to the original vanilla gradient descent algorithm. So this is the reason why many practical algorithms love to use momentum method. And also when you use stochastic gradient descent algorithm, we will discuss what is stochastic gradient descent algorithm maybe in 3 weeks or 2 weeks. Basically, in the stochastic gradient descent algorithm, we cannot access the true gradient, but we obtain kind of noisy version of gradient. And when you learn momentum method, this term actually averaging many iterations gradient. And one good point of averaging is we can average noises. And if the expectation of the noise is 0, we can cancel that. We can decrease the variance of noise by adding many different random vector. So that property make a better convergence property behavior. Okay, so that's why momentum method is very useful in practice. But theoretically, momentum method is not such great. But the Nesterov, some other version of momentum method, another variant of momentum method, is very nice, and we can guarantee better convergence speed compared to vanilla gradient algorithm. Okay, so from now we will study what is Nesterov gradient method, Nesterov accelerated gradient method, and how to show the convergence of the Nesterov gradient acceleration method.